Dear students, I welcome you in this lecture from the chapter Finite Dimensional Spectral Theory. In this lecture, we will study properties which are required for proving spectral theorem. The main purpose of this chapter is to prove spectral theorem. And before we prove spectral theorem, we need to prove some properties. So let us prove the properties of linear operators on Hilbert spaces. So first property is, if T is a normal operator on Hilbert space H, then X is an eigenvector of T with eigenvalue lambda conjugate if and only if X is an eigenvector of T star with eigenvalue lambda conjugate. So we have a theorem which states that lambda is eigenvalue of T if and only if lambda conjugate is eigenvalue of T star is eigenvalue of conjugate operator T star. So lambda is eigenvalue of T if and only if lambda conjugate is eigenvalue of operator T star. Since T is normal operator on H, T minus lambda I is also a normal operator on Hilbert space H, where lambda is any scalar and I denotes identity operator on H. I is identity operator on Hilbert space H. So if we consider T minus lambda I star, it is easy to observe that T minus lambda I star equals to T star minus lambda conjugate I. So with this observation, we have, since T minus lambda I is normal operator, norm of T minus lambda x equals to norm of T minus lambda ix for every x belongs to H. This holds for every x belongs to H. This follows from the fact that if T is normal operator on H, then norm of T star x equals to norm of Tx for every x belongs to H. This further implies that norm of T minus lambda ix equals to norm of T star minus T lambda ix for every x belongs to H. Therefore, we have norm of Tx minus lambda x equals to norm of T star x minus lambda conjugate x for every x belongs to H. It is easy to observe that all steps can be reversed back as well. So we have if and only if type of statement, that norm of T minus lambda x equals to norm of T minus lambda star x if and only if norm of Tx minus lambda x equals to norm of T star x minus lambda conjugate x. So we can conclude that Tx minus lambda x is equal to 0 if and only if T star x minus lambda conjugate x is equal to 0. This implies that x is an eigenvector of operator T with eigenvalue lambda if and only if it is an eigenvector of operator T star with eigenvalue lambda conjugate. So this completes the proof of first property. Let us proceed to see the second property. So the second property is, if T is a normal operator on Hilbert space H, then eigenspaces of operator T are pairwise orthogonal. That is, MIs are pairwise orthogonal, where MIs are eigenspaces of operator T. My question is, what is eigenspace of T? So, eigenspace of operator T is nothing but set of all eigenvectors corresponding eigenspace of T with respect to lambda, I can say, with respect to lambda, where lambda is eigenvalue, it is set of all eigenvectors corresponding to set of all eigenvectors corresponding to eigenvalue corresponding to eigenvalue lambda corresponding to eigenvalue lambda. So it is simply set of all eigenvectors. Now we have to prove that set of eigenspaces is set of pairwise orthogonal sets. In other words, if we take any eigenspaces m1 and m2 are eigenspaces corresponding to two distinct eigenvalues lambda 1 and lambda 2. So lambda 1, the corresponding eigenspace is m1, and lambda 2, the corresponding eigenspace is m2. We have to prove that vectors in m1 and m2 are orthogonal to each other. So if x1 belongs to m1 and x2 belongs to m2, then we will have the relation tx1 equals to lambda 1 x1 and tx2 equals to lambda 2 x2. So consider lambda 1 inner product of x1 and x2. This equals to lambda 1 x1 x2. Lambda 1 we are taking inside here. Then this equals to tx1 inner product of tx1 x2, that equals to inner product of x1 and t star x2. So x1 lambda 2 conjugate x2, because tx2 is equal to lambda 2 x2 implies t star x2 equals to lambda 2 conjugate x2. So by virtue of this property, we are writing that inner product of lambda 1 x1 x2 equals to x1 lambda 2 conjugate x2. So with this we have the conclusion that lambda 2x that this equal lambda 2 x1 inner product of x1 and this equals to lambda 2, here it should be lambda equals to, so this is not this, so this is equal to lambda 2 x1 x2. So lambda 1 inner product of x1 and x2 equals to lambda 2 inner product of x1 and x2. Hence we have lambda 1 minus lambda 2 inner product of x1 and x2 is equal to 0 implies that x1 and x2 is equal to 0, since lambda 1 is not equal to lambda 2, and this implies x1 is orthogonal to x2. This is simply obtained from the previous relation which we have proved. So the previous relation was lambda 1 inner product of x1 x2 equals to lambda 2 inner product of x1 and x2. Thus x1 is orthogonal to x2 for every x1 in M1 and every x2 in M2. Hence we have the property that M1 is orthogonal to M2. So in this property we proved that eigenspaces are orthogonal to each other. Let us study third property. The third property states that if T is a normal operator on H, then each eigenspace of T reduces T. So let us see proof of this. As M is eigenspace of T corresponding to the eigenvalue lambda, so M is, we are beginning with assumption that M is an eigenspace of T corresponding to eigenvalue lambda. Now in order to prove that M reduces to T, we have to prove that M is invariant under both T as well as T star. So as M is eigenspace of T, by known theorem M is invariant under T. All these results we have studied in first chapter. M is invariant under T. Let me repeat it. From the results in second chapter, we know that M is invariant under T. It remains to prove that M is invariant under T star as well. So to prove this, consider x, vector x belonging to M. Then Tx is equal to lambda x, and hence T star x is equal to lambda conjugate x. As M is linear subspace of H and x belongs to M, lambda conjugate x also belongs to M. Thus, what we proved that if x belongs to M, then T star x is equal to lambda conjugate x. Therefore, M is also invariant under T. We already have that M is invariant under T, which we have proved earlier, and now we have got M is invariant under T star. So combining these two facts, we can say that M is invariant under both T and T star, that is M reduces T. So combining these facts, we can say that M reduces T. Thank you.